Okay, let's do an example. An example on heat generation and thermal transport. We're also going to include things such as convection. So in this problem, there's convection along the length of a rod. So we're talking about a 1D model, and we have a functionally graded conductivity we define as this variable k, depends on the position x. So here's our rod. Take our origin at this point, and length of the rod is b. We may have heat flux on both sides. Here's k sub j, k sub I on the opposite side, and we define our width and our height by b and h. We also say that we can apply a current internally so you can generate heat, and then you may also have heat losses through convection on the surface. Alright, so the PD or ODE governing this equation is given here. So you may notice this looks similar to Fourier's law, except here we have a conductivity that depends on position. This is my cross-section area. In addition, we have this heat generation. So Q sub G is the amount of heat flux that's coming in through this coil of wire. And then we're going to have heat convection on the surface. So this is my perimeter. P is my perimeter, H is my convection coefficient. So that's my ODE, strong form of the ODE, and is subjected to boundary conditions. So we have external heat flux on both sides that are based on these. So let's take this strong form, put it in the weak form. So I'm basically taking that strong form equation here, multiply it times an unknown weight function W, and we're going to use integration by parts, or what I like to do is use the product rule and substitute this back in. So if I take the product rule on this thing, so basically I'm taking this, I'm pulling this inside. If I take the derivative, you get a derivative on the weight function, you get this whole term, and then you can also write this as W and then derivative of this whole thing. Of course, you could also have multiple terms, derivative on K, second derivative on this, etc., etc. We do it this way for specific reasons that will become clear in a moment. Basically, because we define this as one whole term. So you notice now this can be substituted by these two terms. And that's what we do here. So I solve for this and I substitute it back in. So now I have derivative on this and this term. So notice this whole thing here is this term minus this term. And then I just bring down these two terms. One thing to note is there should be a W on here. I've made a typo in my notes, but the weight function should be multiplied through on both of these terms. Alright, so we manipulate the equations, rearrange some things. I've written the equation correctly here with the weight function times everything. You can integrate this explicitly. So this is just derivative integrated over dx. So you just have to evaluate this function at the endpoints, 0 and L. So this is the final weak form that we often talk about, and is really the first step in setting up the finite element problem. So you have to deal with this integral or integrand here and subject it to the heat flux boundary conditions on the end. Recall here I have Qj and Qi, which we have already defined here, right? So that's why that becomes important in setting up the weak form. So that is your governing equation.